I was asked by Cynthia Dennis to say a few words about what led to this lecture and the visions that we have for it, and to introduce the speaker as well. So let me get started here. First, I'd like to say thank you to Cynthia Dennis for all the work that she and her office have done pulling this together on a short notice, pretty short time. And also thanks to Audrey Keller, the Physical Sciences Development Officer. I met her for the first time today. We've been able to do all this by email and telephone, getting all this organized. I'm really thrilled to be here. I have one big regret, and that is that Carolyn can't be here. She loves seminars. She was a very enthusiastic participant, especially with the socializing afterwards. She just was electric. So we figured that a seminar would be a nice way to bring her back. Let's see. In addition to introducing the speaker, I've been asked to talk a little bit about the vision and the things that led to forming this lecture series. It's actually called the Carolyn Y. and William S. Rehberg in ESS Endowed Lecture. And this will go on year after year as the money earns money. We're calling it the Rehberg Lecture for short. Carolyn and I were both raised to believe that if you benefited from an organization or some program, that you should find some way to give back. And so for much of our lives, what we've done is volunteered. We've been volunteers in Boy Scouts, Girl Scouts, Nordic Ski Association, or Nordic Ski Division of the U.S. Ski Association when we lived in Alaska. So we've been active doing this. But the trouble is we live 1,000 miles away from Irvine now, so we had to come up with some sort of a different idea. And so what we decided on was a lecture. I think the department needs some sort of a celebration. It needs something to kind of commemorate your stature, how far you've come, and felt that this was an important way to do it. It's sort of modeled after the Lee lecture in chemistry. They do something very similar each year. The number one reason is that I'm so incredibly proud of what this department has grown into. I was one of the founding faculty, and it's come a long way, believe me. It turns out that I regard the 16 years I spent here as probably the best of my career. They were just super, just electric the whole time. And I'm especially proud of the kind of process that we went through when we put the initial proposals together to form this department. We had to write two. One was one that dealt with resources, and this sort of was to be sort of for internal consumption by the university. And then the second one was a department proposal after the first one had been approved. And so we did that, and one of the things that I'll never forget is the way that the initial faculty, we always checked our disciplines at the door. And we all came in and focused on the hard task of producing the best possible new program in a new area or system science that we could. And it looks like we were successful. I think that the NRC rankings bear that out. And all I can say is that something went right in those meetings, and they lasted a long time, and I thought they'd never end, but it was a very, very good thing. What we sort of have as a goal for this, or stipulations about it, were that the first thing is that we wanted the speaker to be chosen by researchers, not just the faculty, not just a committee, but by researchers. And so what Mike Goulden did was to set things up so that 2 research groups each year choose the speaker. And so that I think is I call it a piece of administrative parsimony, but I think that he'd have a hard time getting a big committee together anyway. So that was one thing that I think our initial days were people really run from big committee meetings. The other thing that we wanted this lecture to have was to have a roundtable with students. Roundtables are kind of a tradition, if not a hallmark in ESS, and it turns out that the student roundtables in particular are very effective, and just heard from a speaker today saying, hey, it was great. So that's another part that we want to have. And the third thing we wanted to do is to ensure that the lecture alternated between modelers and measurers. It turns out that from its very beginning, ESS has always had a constructive tension or balance between theoretical and modeling studies and field and laboratory measurements. And I think this is essential for the field. I think the field has neither can exist alone, and it's important to have that kind of tension. So I think it's a good thing. So anyway, today we have a measure. First, the inaugural one is a measure. So what our hope is that the department and the speakers benefit from this celebration each year. I think that should do a lot to keeping the department together as a cohesive group that they're so well known for, a model department in that regard. So we wish you the best. And now to introduce the speaker, Jim White is from the University of Colorado. He was chosen by the Moore and Family Yeti groups as the inaugural Rehberg lecturer. Although it's not present in public forum any place, I learned last night that he was raised in Tennessee, bachelor's degree in chemistry from Florida State. He went to Lamont, Columbia University. After Columbia University, he spent several years in Europe working with the CNRS lab at Gif-sur-Yvette in France. He came to the University of Colorado. He's presently head of the INSTAR, the Institute for Arctic and Alpine Research. He has academic appointments in geological sciences and environmental sciences. He spent a big chunk of his time getting this environmental sciences program off the ground. The title of his talk is going to be Ice Core, Sea Level, and Abrupt Climate Change. You've probably all seen an abbreviated abstract, but he's going to be talking about the latest findings from the Neem core. The Neem core is one that's a very deep one that basically drilled through the Eemian into the previous glacial period. And so he's got basically going to give us a talk about the results from that core work. So with that, I give you Jim White.
How does one begin an inaugural lecture? Not that way. Right? Need to be a little snappier. I mean, I am honored to be here. I've known Bill for quite a number of years, and he and I have talked about a variety of scientific topics all of our lives. Not all of our lives, but for quite some time. And it is an honor to be here. I think the world of him, and I actually think the world of you guys. I mean, I think of, there's probably only a few places I could ever be happy, and you guys have one of the best faculty on the planet. And this is probably one of the few places that I could find myself really thriving and having a lot of fun. And having a lot of fun, as I talk to the students, is what it's all about. So I don't know how a good old boy from Texas and a good old boy from Tennessee ended up being today's entertainment, but that's what you've got coming. So I'm going to talk to you basically three talks in one. The first is going to be a look at the latest information that we have from the latest of our Greenland deep ice cores, the Neem deep ice core. That will transition into a brief but hopefully entertaining midsection, sort of the middle course, on looking at sea level and in particular what I like to do when I talk in public about sea level. So we're going to go from a strictly scientific kind of talk to one in which we spend a little time talking about things that I would say were this a public lecture. And then we'll shift gears back to science and talk about abrupt climate change, and in particular some of the challenges that I think exist in that arena. I would start out by saying I first thank you all. I've had a great time so far, and I hopefully you will have a great time over the next hour. I've already had at least one person come up to me and remind me of an evening that had way too much wine involved with it in Paris. So you never quite know what's going to happen in life, so just let it roll. All right. I have some co-conspirators on this talk. Dorte Dahl Jensen is the head of the Ice Core group at the University of Copenhagen, the Center for Ice and Climate, and she has her fingerprints all over the slides I'm about to show you. Trevor Popp is an ex-PhD student of mine. He and I have worked together on abrupt climate change. He now works for Dorte. Bo Winter is the heir apparent to Dorte's lab, and Sigfus Janssen, who I will show a picture here pretty soon, is a very dear friend of mine who just recently passed away. And it is to him that I owe a lot of what I do. For those students in the room, you know that there are people in your lives right now that are helping to shape you and helping to send you in directions, and treasure that, because those are the people that are going to be lifelong friends. And Sigfus was one of those people for me. So we're going to be looking at the Nîmes deep ice core. It is important to recognize that we have a series of ice cores now. When I got into this business, the list stopped right here at die 3. We've added 4 deep ice cores since then. This is actually a pretty big place. So what I'm going to show you is still very coarse resolution. Still quite a bit about Greenland we don't understand, about climate in Greenland, about the ice sheet in Greenland we don't understand. And a lot that we need to learn, and I wouldn't by any stretch tell you that we've Swiss cheesed it enough to understand how it works. But these are the ones that we're going to be looking at today. In particular, I want to point out, I'm sorry for the print size, North Grip here and the Grip and Gifts 2 central deep ice cores here. The only one we have in the south right now that goes all the way base is die 3, going back into the 1980s. So the big picture. So the Greenland ice sheet is somewhere in the neighborhood of several million years old. We know that from a couple of lines of evidence, one of the probably the best of which is that's when sea level began to change in a way that accounts for that much ice. But we have the occasional bits and pieces from the bottom of the ice sheet that give us the confidence of saying it's right around that time. The oldest ice, on the other hand, that we found so far dates just into the last interglacial period. This is the North Grip ice core shown with the Grip ice core. And you'll see a couple of things on here. One is, and I apologize, this is not time. I have the wrong slide in here. But this is the last interglacial period. We just got into the last interglacial period in the North Grip ice core. Tantalizing little piece of it that turns out to be very, very important for the story I'm going to tell you here. But also note that the abrupt change is the hallmark of this record. And as little as 20 years ago, we argued over whether these were climate changes or whether there were some other features that we're looking at in the ice core, whether there's something wrong with our ice core, whether or not this was something fundamentally strange about ice cores. It wasn't until we found these changes, not only in many, many ice cores, but we found these types of changes existed in many, many properties that we could measure, including, for example, temperature changes, that we began to realize, yes, indeed, that these things were climate. I'm going to come back to this, but I want to point these out over here. These are abrupt climate changes that occurred during marine ice stage 5. And that's important because we'll come back to that. That's a time of, it was cooler than today, but it was, ice sheets weren't enormous. This is the beginning of the glacial period. In many ways, still kind of an interglacial time period. All right. So what were we after in the Nîmes ice core? In the Nîmes ice core, we had 2 major goals. One was to look for the last interglacial period, also called the Eemian. The other was to verify, and I'll show you what I mean by that, and improve the previous records that we had. This is, as I pointed out, the Nîmes ice core is farther north. It turns out there's a north-south gradient in the Greenland ice sheet, and we had seen this in the other ice cores, and we wanted to get some better idea of what that was like. Times have changed. When we first started to do ice coring here, particularly in central Greenland, melting was unheard of, basically. And there's very, very few melt layers that you can see here, particularly in central Greenland. It's gotten much warmer. I don't know if you folks have noticed that, but that was a joke, kids. Come on. You got to play along here. It's gotten much warmer, and something really interesting happened in July of 2012 that really experienced Greenland ice core researchers had never seen before, particularly on the top of the ice sheet, and that is a rainbow. You see snowbows every now and then, but a rainbow requires some liquid water, and that was a real stunner. It actually rained up at Nîmes. We had melting and on July 12th, pretty much all of the Greenland ice sheet had surface melting, but we actually had rain at Nîmes. Now this turns out to be I won't go deeply into it, but this is a fundamental problem for us because we like it cold. We like it cold because the ice we pull out of the hole needs to be cold and stay cold, and this is a challenge for us. The other challenge for us is that we get in and out of this place in large C-130 Hercules aircraft with skis on them. And for those of you who ski, you know that if you're skiing on snow that's wet and sticky, you don't go very fast, and neither do airplanes. And they can do such fundamental things to you as say, I'm sorry, but there's not enough power to get this airplane off the snow surface. We're going to have to leave you behind. And they do that occasionally. So we have debates about what's more important, retrograding ice cores or retrograding scientists. But hopefully we won't get there. So why look at the last interglacial period? It is interesting for a number of reasons, but I think the most fundamental reason, the one that I get most excited about, is that it is one of our analogies for the future. We have a couple of analogies for the future, but this is one of them. We're looking at a time period of roughly 120 to 130,000 years ago. It was warmer than today by a couple of degrees, which is obviously an analog in a sense in that we are in a warming world. Sea level was higher by something in the neighborhood of 4 to 8 meters, and I'll show you some other numbers there. And that's where we're going as well. As time goes by, sea level's rising today. It will continue to rise today. We'll talk about that in the mid part of the talk. And there was a smaller Greenland ice sheet, and I say in model world because we don't really know. This is what we were after in the NEAM ice core. Could we indeed say something about the size of this ice sheet in the past? And the speculation was there was a loss of ice somewhere equal to about 4 meters of sea level rise. So can we indeed verify that? And that's what really we were after in the NEAM ice core. This just shows you that the last interglacial period is not a perfect analog for the future. It was warmer because summer insolation was higher, not because greenhouse gases were higher. Greenhouse gases were maybe around, CO2 was about 300 parts per million, so it wasn't much above the 280 ppm baseline that we see for the pre-industrial period. So it's not a perfect analog, but it's still the best shot we have. It's the closest analog in the past. Sea level during the Eemian was higher than today, as I pointed out. There have been a number of studies recently. In 2009, Kopp et al. Did a statistical study where they took all of the observations, put them together, and estimated that sea level peaked, as I say here, somewhere around 124,000 years ago, roughly 7 plus or minus 1 meter higher than the present. For those of you who've been to the coast, imagine 7 meters above you, imagine 20-something feet above your head. That's where sea level was. And they concluded there were contributions of something like 2.5 meters from both Greenland and Antarctica. And that's important, and I'll stress why that is true in a few slides. So there have been a number of modeling studies that have looked at the Greenland ice sheet. A recent one by Robinson and group in Climate of the Past, where they looked at various realizations of the Greenland ice sheet. In this case, they took, as it says here, 360 simulations, 90 model realizations. And of those, they took 46 simulations from the 20 model realizations were selected based on the criteria you see here, that mass balance was in agreement with the present, observed the model, the surface model had to be right at grip, which was the center of the ice sheet here. And there had to be no really large loss of ice, as some models get when they look at the Greenland ice sheet in the past. And these are typically models that are driven primarily by insolation and by greenhouse gas levels. So you're looking at basically the impact of summer insolation on the Greenland ice sheet. So the conclusion was that the Greenland ice sheet lost mass and was somewhere in the neighborhood of about the same to as much as 4 meters sea level equivalent less in its mass in the past. So roughly about the same as that 2.5 meters that we see here. So what do we observe? One of the interesting things was we were able to measure the ice core in the field for the first time. And I'll come back to this, but this was a breakthrough. We have what we call continuous flow analysis. So if you've never been on an ice core site, we take the ice core, take it down from right out of the drill. We let the liquids evaporate off the surface of the drill fluid, and then we take it back, and if it's cuttable, that is if it's not in the brittle ice zone, and we can get into that detail if you want, but basically, then we slice the ice core, and we begin to analyze it. Right then and now, we have what we call a continuous flow analyzer that measures chemistry. It's a melt head. You just take a stick of ice, put it on top. We can also measure stable isotopes. So in real time, we know where we are in the ice core now. And that wasn't true in the Di-3 ice core, and it wasn't even true in the GISF-2 or GRIP ice core. This is only in the past couple of ice cores have we had the capability of knowing where we were as we were actually measuring this. So we knew that up to about 2,200 meters, everything was right, because it looked just like North GRIP, or not just enough like North GRIP that we knew everything was pretty normal. Past about 2,200 meters, things began to get really weird. And this is the actual records here. You see the 018 of the ice was cruising along. The colors are color-coded for a reason you'll see in a minute, but obviously they weren't color-coded when we got them. And so they were cruising along. We saw what we thought was a pretty clear chunk of the Eemian. There was some craziness down here at the bottom, things bouncing around, and then we hit bedrock. The second analysis you see on this, which is important one, the del 018 of the atmosphere. So the oxygen 18, oxygen 16 of the O2 of the atmosphere. That's important because that's one of those measurements that has to be the same in all ice cores. So if you measure it in Antarctica, since it's a common atmosphere and the atmosphere is quite well mixed, particularly for oxygen, you know that the del 018 that you measure in Antarctica has got to be the same as the del 018 of O2 that you measure in Greenland. So this is a very important measurement for us. Methane, we also measure. Methane is obviously a very important greenhouse gas, but it's also one of those gases that, while there is an interhemispheric gradient to methane, it's also got to behave basically the same between all ice cores. And so methane is something that we use to synchronize ice cores, that we use to put ice cores together. So we measure that, and that's measured in real time. Nitrous oxide is the next measurement you see here. And then there's a couple others at the bottom I'm not going to get into very much, other than point out that we do measure air content, which is a rough proxy for how high the ice sheet is. What we noticed immediately in the field was that a couple of things. One was methane had these huge spikes. And that's wrong, because those spikes don't show up in other ice cores. They didn't show up in Antarctica, where we have ice cores from this time period. And so we knew that we had some problem here. Now, the problems weren't huge, because this, as I'll point out in a minute, is consistent with melting. And what this told us was that probably the Eemian was significantly warmer than it is today, because we don't see lots of melting today. But we do see lots of melting during the Eemian. So that's an indication that, indeed, it was much warmer. Nitrous oxide was basically telling us the same thing. What we also knew right away was that the del 018 of the atmosphere did not look right. And so we knew that we had trouble with the ice core. There was something fundamentally wrong. Now, we did a lot of work prior to drilling the ice core in looking at radar echo layers in the ice sheet. This is a slice from Nîmes. Here's the northwest corner of Greenland. This is the ice divide here. And you see with the flow direction coming here that you see, you can look at these radar echo layers, and you can see that they're nice and flat. And that's what we like to see when we go in and drill an ice core. And the technology at the time we started Nîmes, we could actually see that everything looked layered. It looked nice. I remember we had long arguments over whether or not there was any kind of turbulence at the bottom, any kind of problem at the bottom. And at the time, with the best radar that we had, we couldn't see any problems. And so we thought we were in pretty good shape, or we thought we were in as good a shape as we were going to be. This is a later picture from Prasad Goganini's group in Kansas. And you can see that had we had really good radar, we would have said, hey, wait a minute, there may be some fuzziness at the bottom. And whenever you get fuzziness in radar echo layers, you get a little nervous. This shows you what you really get nervous about. Right? This is a picture on the north side of the ice divide. And here we have these are layers which are quite traceable from one ice core to another. For example, we can trace this from North GRIP, where the thing is dated, and we know exactly where we are. Here you can see at 84,000, you can see some really interesting folds and dips in the ice. Flow direction in this case is going in this way. At 100 and something thousand years ago, we know that this is roughly the 109,000 threshold, and you can see all sorts of bumps and wiggles in here. So as technology has improved, we're now able to see, yes, there's problems in this area. If you go a little bit to the south of the Nîmes area, you can see even really fantastic features in here. This, by the way, is the reason why I'm now writing the proposal for the next big ice core. And until we actually map all these radar echo layers in the ice sheet, we're not going to go back and try to drill a deep ice core to get the Eemian, because obviously we need to know exactly what's going on, and figuring out all this interesting folding in here is something that we're going to need to deal with. So basically, a long story short, what we discovered was that this record I showed you before, and the color coding is still the same, had a couple of pieces that were upside down and repeated. So the ice had folded over, and I'll show you a little movie of what we thought happened. But basically, the ice had folded over, and we ended up drilling through it more than once and having a piece that was upside down. Okay? Now, how do you know that, right? So one of the challenges is you've got this scrambled record, and those of you who are geologists and you go out in the field and you look at rocks. Do you guys do that at all around here? Okay. Maybe not. Anyway, they do that, right? Geologists go out and do that. And they look at rocks, and they see all the folding and stuff, and they try to put stuff back together and try to get the deck of cards, if you will, stacked back up the way that they would have otherwise. And so we spent quite a bit of time arguing about it. I remember Dorda was in my office for a couple of days, and we plotted things differently. We messed around with things. Basically, what you want to do in order to make this, put it back together, is you want to plot things that you know have to be correct, and in a sort of like a phase diagram. And then you take what you've got and see how it lays on there and find the most logical way in which the pieces go back together. Okay? So fortunately, what we had from North Grip was we had the Del-O-18 of air we talked about, methane and the Del-O-18 of ice, and we are able to plot in a three-dimensional space the evolution of what the North Grip ice core looked like. So in this, we know that the North Grip was not folded at the bottom, and the reason for that is a little more complicated story, but basically it's melting at the bottom of the North Grip ice core, and so the ice never gets a chance to fold there because it never sticks at the bottom. It just keeps melting off the bottom. And so we knew that we had to match this particular phase diagram, and this is what we got when we added the NEAM. So now you see, by the way, the methane scale has been expanded, which is why that three-dimensional diagram I showed you before has now been collapsed. And you see almost all the information we saw before is now collapsed into the lower end of the methane scale. Because we have these high methane peaks, for example, we know that this can't be right. And you can see over here where those high methane peaks are. But everything else, and I'll now show you one slice through this, everything else made sense. If we inverted those two pieces and we put them back together correctly, or put them back together the way we think is correctly, this is what we got. The only thing that really doesn't fit here is that methane is too high. Now, and for reasons I can't go into because it's a long story, but basically that's consistent with melting during the Eemian at this site. When you melt, you end up enriching methane. By the way, the CO2 is completely screwed up, so don't even talk to me about that. But basically, methane is increased, and it's increased by roughly 50 ppb shift in the baseline, and by a whole bunch of high values that we know are not realistic, but still are possible given a certain Eemian level of methane and then with melting. Keep in mind that if we saw really low values of methane, that's a lot harder to explain. Right? So that would imply that the ice, there had to be some glacial ice or something there that had even lower methane to begin with. So the phase diagram actually puts back together correctly with the pieces, as I pointed out, flipped around and backwards. Oh, I forgot this was in here. So Dorda had this little movie made. So this is actually what we think happened, artist rendition. So you see, for example, as ice flows along, as it flows over bumps upstream, you tend to form these bumps, and those bumps continue. And then you can have what we call shearing, or you can rip off pieces of ice as you have differential flow, one piece flowing faster than another. And this is one possible, actually probably the only possible way in which we think that you can put back together the record that we found. So you have folded pieces, you have sheared off pieces, and you have repeated pieces. And you can see that some of these pieces then have to be going in the wrong direction time-wise. If you put this back together, invert the pieces, and then compare it to ice core records that we have from Antarctica that we know aren't folded and that we know are correct, this is the record that you get. Focus, if you will, on the Del-O-18 of atmospheric O2. So this is the EDML, the Epica droning modland core from Antarctica. That's a record that we know we have to match. And so now with the pieces that we've put them back in the way that we think makes sense, the del 018 of the atmosphere makes sense. Methane makes sense, although it's high. And that's our melting problem there. Nitrous oxide makes sense, but it's high. And here you see the del 018 of ice, by the way. It cruises along. And these two can deviate because the climate of Greenland is not necessarily the same as the climate of Antarctica. So this is not a problem up here. This is a real reflection of the fact that we wish we had more ice in here because we think that we know that the Eemian began, we're missing some of the Eemian, in other words, or that the last interglacial period in Greenland was not exactly the same as the last interglacial period in Antarctica, which would be an interesting surprise. This is one of the reasons why we really do want to go back. We really do want to find a place where we can get out of the folds and get the full record of the last interglacial period. So in a nutshell, in this first third of the talk, these were the two big take-home messages that we got from the NEEM ice core. One was that the temperature, and this was temperature reconstructed from stable isotopes and from other methodologies that we can talk about later, but the temperature was roughly about 8 degrees warmer than it is today, consistent with lots and lots of melt layers that we don't see today except for July 12th of last year. And we can also tell that Greenland did not contribute more than roughly 2 meters to the sea level rise of the last interglacial period. So we can tell from the climate, we can tell from the height of the ice sheet that indeed this locality could not have been terribly different, only by maybe a couple hundred meters maximum different than it is today. And so that constrains how the rest of the ice sheet must have been shaped at that time. So when we first had this result, we had a lot of argument among the principal investigators about what this means. There were some people who were rather sad that the Greenland ice sheet had not contributed more to the last interglacial period's sea level rise because they wanted Greenland to have a wonderful statement. They wanted Greenland to be important. Let's face it, while we're scientists, we care, right? I was actually kind of happy because if Greenland's not contributing to more than a couple meters to that sea level rise, that means Antarctica was contributing. And I view Antarctica as the unstable child in the family of ice sheets, right? This is the one you really got to watch out for. This is the one that could go postal on you. So the fundamental question is, if Greenland did not contribute more than 2 meters to sea level rise, where'd the rest of it come from? And the answer has got to be Antarctica. Now I'm going to take a moment here and go into some stuff that I know is very simple for you folks, but I think it's interesting to take a step back and think about this. One of the things that as a scientist, this has sort of been, I know this and you all know this, that we live on a planet in which ocean water is traded for land ice and vice versa. But I really have never heard it expressed like that. It is indeed a trade-off. That when the planet cools off, water comes out of the ocean and is dumped on the land and stays there. And sea level remains low. And if the planet warms up, that ice begins to melt and the water flows back in the ocean. Right? And it sounds so simple, but if you go out to the average person on the street and you ask them, talk to them about sea level, they will tell you it's level. And they will tell you, no, it can't go up very much. And the idea that sea level could rise by meters, or say a meter by the end of this century, just sort of shocks people. But as scientists, we know that that's not the case. Our planet is very dynamic, that sea level goes up and down by hundreds of meters. And that this is probably one of those basic lessons that we need to get out there in the public and talk more about. We need to get people alerted and softened up to the idea that sea level can go up by a lot and sea level can go down by a lot, and that all that expensive stuff you built on the coast can either be left high and dry or it can be drowned. Right? So, how fast sea level goes up and down is the other part to the story, and this is where our knowledge lies right now, and really clever people like Eric and others are looking at how do these big ice sheets behave and how rapidly can they shed ice and put that ice in the ocean. Antarctica is an interesting chunk of ice. West Antarctica, I'm showing you the bedrock because West Antarctica primarily has a bedrock well below sea level, thousands of feet below sea level. Also chunks of East Antarctica, Eric and I were just talking about this, there's large chunks of East Antarctica that also have a bedrock which is well below sea level, which means that you've got an ice sheet that is held back by just pinning itself to either some sediments or a few islands or an ice shelf, but something is holding it back, right? And that's critical because for marine-based ice sheets, I don't need to tell you folks this, but for marine-based ice sheets, having that grounding line is absolutely critical. Getting it to stop against some sedimentary point, against some rock, against something that keeps the ice sheet pinned there is critical for the stability of that ice sheet. Now, as sea level rises, obviously you've got trouble because your ice sheet's going to rise a little bit. But also the big issue is as you warm the water up, and this is something that Eric and others have been really champions on, is trying to figure out just how important warm water is. And warm water is hugely important. Warm water comes in, can erode to the base of the ice sheet. You lose that pinning point. And what we don't know is how rapidly could something like West Antarctica or those marine-based chunks of East Antarctica shed ice into the ocean and raise sea level. We know from looking at the history of sea level in the past that sea level has gone up by much faster than it's going up today. Today it's going up by roughly, we expect maybe a meter by the end of this century. It can easily go up 3 times faster, 5 times faster, even 10 times faster in the past. And that's important. As I was talking to students today, keep in mind that a meter by the end of this century, while that's shocking, and I'll show you pictures of why it's shocking, keep in mind that the end of this century is a long time off. All right? If sea level was going up 3 times faster, in other words, if you were looking at a meter rise of sea level within the next 30 years, within the average time of a mortgage, let me put it that way, then that changes the way people look at this. That changes the way people think about it. So the pace of sea level rise is extremely important. And one thing we know is it's going to go up. And really the fundamental question is just how fast is it going to go up. So the question is not whether if sea level will rise in a warmer climate, but how fast and how far. My poster child for sea level rise, and this is now where I'm talking a little bit to you as the public, my poster child is Miami. And it's because Miami is indefensible. Miami is built on sand and coral. Miami has spent quite a bit of money hiring Dutch engineers to come and take a look at their problem. And the Dutch, being very clever people, said, fine, pay us. And then they said, I can't do a damn thing for you. I'm sorry. Because we really can't build dikes around Miami. It isn't going to work. This is Miami with 3 feet of sea level rise. Roughly what we expect by the end of the century. This is not a city that functions anymore. This is a city whose gas lines, whose sewage systems, whose electrical systems are compromised by salt water or completely cut off by salt water. This part of Miami is intimately connected with this part of Miami by infrastructure, et cetera. We all know this. Big cities aren't just little pockets of isolation. So really Miami has about 80 years, 100 years left. Now, if that makes you sad, keep in mind that 100 years ago, Miami was a swamp. All right? So Miami's got about a 200-year run as a city. All right? Now, and I actually had the wonderful honor of going live to the folks of Miami, because I go to a conference every year in which we try to bring in TV weather forecasters from around the country, and we talk to them about things like climate. And so one of them said, I gave this talk and I showed this particular slide and said, well, I want you to go live to the folks in Miami and tell them what's going to happen. So I did. And he actually said, he said, what's the prognosis for the city of Miami? I said, you're toast. And that did not go over well. Right? Anyway, really Miami doesn't have much of a future beyond this century. And Miami's certainly not alone. There's a whole bunch of cities along the coast. This is Miami with 2 meters of sea level rise. And I show this to you because keep in mind that sea level is not going to go up a meter and then stop there and go, whoopee, it's 2,100. It's going to keep going up. Right? And we all know that that's going to happen. So how much higher is it going to go up? And so the paleoclimatologist in me asked a very simple question. Can I look into the past and find a time when there was roughly 350 to 400 million parts per million of CO2, when the continents were about in the same position? And the answer is yes, I can find a time. It's roughly 3 to 5 million years ago. At the Pliocene, it was a much warmer climate. There were trees growing up in the Arctic Circle, and very importantly, sea level is about 20 to 25 meters higher than today. So if you do something simple like Dave Archer's done here, many other people have done this, you simply plot global mean temperature versus sea level. You see that while these things don't fall perfectly on a line, in general, there's a very strong relationship between sea level and temperature on a planet because the physics are so simple, right? You warm up the planet, you warm up the water, you start to melt the land ice, you start to shed this stuff into the ocean. Our planet trades ocean water for land ice all the time, back and forth. There are no points that live out here other than the IPCC forecast for the year 2100, and there are no points that live out over here because that's not the way the system functions. We know, as paleoclimatologists, that if we just sit there long enough at 400 parts per million CO2, it's got to go up. And the best guess would be it would go up 20 to 25 meters. So what does that look like? All right. So this is one, this is one area of the United States with 20 to 25 meters of sea level rise. And this is where I would encourage you to think about this not in a gloom and doom way, but have some fun with it, folks. What's really important right here? Class? Disney World, absolutely. I looked on the topo maps. You can sail the Disney Princess right up to the door of the Magic Kingdom with 20 to 25 meters of sea level rise, all right? Disney's going to work even better than it does today, right? That's important. That's fun, right? You could actually sail, by the way, you can also come down the Jacksonville River drainage from the north as well. So Disney's got a whole, and in my critical thinking classes, I asked my students then to think, who is benefiting from climate change? Think about it. It's Disney. Who's behind climate change? All right, I'm not going to go there, but you ponder that. There's some interesting parts of the United States under 20 to 25 meters of sea level rise. This is one of them. This is the, you all know where this is. There's a chunk of real estate right here that is probably going to be worth a lot of money because that's the choke point between the ocean and land for the Central Valley. This is my favorite, and you'll know why in about 30 seconds. What state is this, class? Delaware. Very good. What was the first state of the Union? Delaware. And they're very proud of it. Delaware signed on the bottom line first. If you didn't know that, shame on you. Go back and study your American history. If you remember nothing about today's talk, you will remember this. First in, first out. You can remember climate change and sea level just by FIFO, okay? Drill that into your head. First in, first out, Delaware becomes a swamp. Okay. For what it's worth, we're at 400 parts per million CO2. Roughly now, it's like 392 actually average global. Mauna Loa hit 400 and we had a whole bunch of celebrations, but then photosynthesis happened and drew it back down again. I think we're going to get to, I mean, we probably ought to put money in a hat and start betting about where we're going to go. I think 600, 700 is an easy. I think really the over-under is right around 800 parts per million. So, and I'm willing, you know, if you want, we can put a basket on the table and start throwing dollar bills into it and see where we're going to be. As it turns out, you know, if you go to 800, 900 parts per million, you start to get back to really interesting times on the planet. You start to get back towards Eocene times when Antarctica didn't exist. So if you let the planet sit for long enough at those CO2 levels, you let it bake long enough, and that's, you know, we're talking a long period of time here, but, you know, eventually. Then this is the sort of thing you get here, and it's not just Delaware anymore, but it's other states that become uninhabited. For those of you who are geologists and who are like paleo shorelines, by the way, you can go and you can find these paleo shorelines all along the east coast of the United States, because 3 to 5 million years ago it was a stable enough time period that you can find those shorelines. You can actually drive down the Interstate 26 and then it goes goink like that. You get the same goink, by the way, if you're cruising along here. So somewhere about halfway through South Carolina, there's this odd feature on the interstate where you just go, oh, I wonder what that was. Well, that's an old beach line from when there was no ice on the planet. And this area of the world happens to be stable enough that tectonically it's not going up and down quite a bit. So you can still find these things. Kind of cool. All right. So now I'm going to wrap up here with a little bit of information about abrupt climate change. I'm going to give you some observations and some ideas, but no answers. All right, so off we go. Again, we're going to stick to these ice core sites. The new NEAM site, the North Grip site, and the GISP2 and GRIP sites we're going to take a look at. So what I've showed you before was a picture of ice cores used in the big picture. That is saying, what did the Eemian look like? And I didn't try to drill down any farther than, say, plus or minus a few hundred years to maybe 1,000 years in terms of climatology. Just trying to understand what's the big picture. Now, one of the cool things about ice cores, and particularly Greenland ice cores and other areas like West Antarctica where accumulation is high, you can get down to the year looking a long time into the past. I have a graduate student today who's looking at the West Antarctic ice core, and at 40,000 years he can still see annual signals in the ice. Can't see them in the isotopes anymore because the accumulation's not high, but you can still see them in chemistry and in other properties. So in Greenland, we can see annual layers going back about 60,000 years. There are actually some Danish graduate students who sat down and counted those. What's important here, I'm going to show you some details from what we'll call the end of the Younger Dryas, which was the last hurrah of the glacial period. It was the last time that the Earth, or at least the northern hemisphere, went back to cold and then came back out of it. At the end of the Younger Dryas, we were off to the races in terms of the Holocene. The start of the Younger Dryas, we all talk about the Younger Dryas as this really threshold event, this last hurrah of the glacial period. Interestingly, we don't really know why. Well, wait, put it this way. The beginning of the Younger Dryas is not that well known. The end of it is quite well known. We have a theory for how it might have started, shutdown of North Atlantic deep water. We don't know why it ended. So as it turns out, this is kind of an enigma. We know a lot about the ending of it and not much about how it ended or why it ended. We think we know a lot about how it began, but the beginning of it is actually not that well defined in the ice core. So. The bowling warming is another piece of time period we're going to talk about. This was another very sharp warming about 15,000 years ago. Now, one of the things I'm going to talk about here is the importance of big ice sheets. So one of the arguments that we have frequently among the ice coring community and abrupt climate change is note that these features occur when there were large ice sheets. Sea level was much lower. So is the presence of the Laurentide in the Fennoscandinavian ice sheet, is that what it requires to have abrupt climate change? That's a fundamental question. If you don't have those big ice sheets hanging out there, in other words, if you're not in a glacial world, can you have abrupt climate change? And one of the messages that drives that is this, and I apologize for I don't have the right, I have a depth and not time. This event is 8,200 years ago. This is called the 8.2 Ka event. That was the last time that we think we had an abrupt climate change of magnitude on this planet. And you can see that it was not very large compared to these things in here. And so that's what, in part, has been driving this debate about whether or not, do we live in a time when abrupt climate changes could actually occur? I would point out to you that these back here, these are ice stages, but don't worry about the numbering. These are abrupt climate changes. They occurred at a time when there was not large ice sheets. There was more ice, land ice today, or more ice, land ice then than there is today, but not by that much. So this is the 110,000 years ago or so. And so we still had abrupt climate changes at that time, and we don't know why. If indeed you'd need large ice sheets in order to have abrupt climate change, and I'm going to give you an idea of why that might be the case. We don't know why these things would occur. So after trying to make the case, I'm going to come back and shoot myself in the knees. These abrupt climate changes occur not only in stable isotopes, they occur in a whole bunch of parameters. You'll see here, this is at the top, the Delo 18 of the ice showing the abrupt climate changes. We can also measure these things using the relative diffusion of air isotopes, which is a pretty straightforward physical way of estimating temperature change. And so you can see these temperature changes are in the neighborhood of 12 degrees, 9 degrees, 10, 12 and a half, 8, 12 and a half. So these are fairly large steps. And I'll scale 12 and a half to 10 degrees Celsius for you in a minute here. A A little history. I got involved in this. I was thinking for this inaugural lecture it'd be important to loop myself back to where I was as a graduate student. So I was a fresh graduate student. This was my first postdoc. I went off to Europe to work with Jean Jouzel. And just before I left to go off to work with him, I was going to work on the Vostok ice core, this famous ice core that no American could possibly be an author on, by the way. We won't go there. Anyway, I went to work with Jouzel. And just before I went, Willie Dansgaard contacted my advisor, Wally Broker, and I said, I want somebody to measure isotopes, deuterium isotopes, in these ice samples we're looking at. And Wally said, well, Jim White's the guy to do it, but he's going off to work with the French. The French did not talk to the Danes. Right? That didn't happen. So Lillian Merlevad, who was head of the French lab, didn't talk to Willie. And so it just possibly couldn't happen. So I ended up, I think at the time, calling Willie because the email system wasn't all that good and people were actually sending letters at that time, believe it or not. And he said, no, it's okay with me if you measure those samples in France, as long as it's okay with the French. So I went and I talked with Jean, and he said, you can do it, but you have to do it at night and you have to do it on the weekends. So I could do it. All right, that was the important thing. So we ended up getting some really fantastic data. This is the first time we'd ever really chopped an ice core up into year-by-year pieces. So we're looking at year-by-year changes. This is roughly 12,000 years, 11,000, 12,000 years ago. And we looked at these things in year-by-year pieces. So we could actually tell that over a period of about 20 years you had changes. Over a period of about 50 years, this warming right here occurs over a period of about 50 years. And that we still know that to be the case, although I'll tell you that things have changed a little bit. I would also point out that Willie passed away a few years ago. He was a great guy to work with, irascible and wonderful character. And Sigfus was just a gem of a human being and will always be near and dear to my heart. And the three of us co-authored this paper that really got me going as a scientist. So as I said, treasure those folks who are your mentors today, graduate students, because they will carry you throughout your career. What are these changes like? They're remarkable. In this case, there was a 10-degree increase in temperature in 50 years. I just pointed that out to you. Snowfall rates doubled in 1 to 3 years. So if you look at the layer thickness, which we can do, cruises along for 1,000 years at some level, and then in 1 to 3 years it bumps up to another level, and it stays that way for 12,000 years. Right, so these are fundamental step changes in the system. Sea ice retreat, by one of the things we measure, we think indicates sea ice, and that also occurred in 1 to 2 years. Methane went up 50% in 50 years, and nitrous oxide went up 10% in 50 years. So these are fundamental changes in the climate system, fundamental reorganizations in the system. I told you I'd scale what is 10 to 12 degrees. The difference between Atlanta and Minneapolis, mean annual temperature is about 9 degrees. The difference between Mobile, Alabama and Minneapolis is about 12 degrees. Right? Now keep that in mind, because I'm going to take you and take that 50 years and shrink it even more. But the changes don't. The magnitude of the changes won't change. So imagine going from Mobile, Alabama to Minneapolis, okay? Climate-wise. Maybe culturally too, who knows? What is signal and what is noise? One of the things we can argue about is if we go and we look at these ice cores, if you're looking at a year-by-year kind of change, what's real, what's signal, and what's noise? This is the North Grip ice core and the GIPS 2 ice core, so from here to here, which is a fairly large distance, hundreds of kilometers. These are the year-by-year changes that you see, and you can see that indeed we're looking at quite a bit of common signal here. These are large changes. And one of the so if we were to actually look at two ice cores side by side today and look at year-by-year changes, you wouldn't see nearly that kind of correlation, because you're not looking at that kind of magnitude of change. So these are very large changes, and clearly something fundamental happened over the ice sheet, and you can see it in a number of different places. Now what we've noticed as we begin to collect more and more of these ice cores, here we have North Grip, GIS 2, and GRIP all plotted together. And I'll show you another plot in a minute, it's even better. But basically what you can see is that somewhere a change happened, and this is actually recorded by a number of things that we measure in the ice core, but one of them is a combination of isotopes called deuterium excess. I won't go into the details of that, but basically we consider that the trigger point. What we think happened was that at some point a change happened, and the system rapidly shifted to a new state, and apparently sat there for a while and then rapidly shifted again. So instead of that being 50 years in going from here to here, we can now say that that is about a 5-year change, plateau for about 30 years, and a 5-year change again. So in other words, you're getting about a degree C per year for 5 years. Now I'll scale a degree C per year for you. We've had a degree C over the last 100 years, roughly. So you're looking at a warming sustained over about 5 years of about 100 times faster than the warming we see today. All right, so this is a fundamental shift in how the system behaves. So that's abrupt. Now, there are examples in Greenland of even more abrupt, what I would call stunningly abrupt. As I pointed out to you, there was a bowling warming, which was a warming period. At that point, and here I have two ice cores, the North Grip and the Neem ice core. The isotopes cruise along and they shoot up, and the time period over which they shoot up is only about 1 to 2 years. And the same 10-degree change occurred, but at this location it occurred in about 1 to 2 years. So you're looking at somewhere in the neighborhood of 5 to 10 degrees C per year. So something just, you know, I use the analogy with my students that, you know, we have all heard this story from our parents. You know, when I was your age, I had to walk uphill to school every day through the snow. It was uphill both ways, right? Because the way the earth worked, right? There really was a time when, you know, Zog had to walk through the snow and little Zog didn't, right? And maybe this is one of those collective memories that we have, you know, in our human psyche. Maybe we're just still remembering the end of the Younger Dryas. Who knows? Anyway, you're looking at something about 1,000 times faster than current. So really something that you know, we struggle to understand. They're not all the same. This is the bowling warming at GISP2 and at North Grip, and you see, for example, that I believe green is the GISP2. It's 50-year transition in the middle of Greenland, and it's only a 1 to 2 year transition in northern Greenland. So there's something fundamental about northern Greenland and middle Greenland in terms of how climate works and how the system behaves. Note that North Grip and Neem, which are both northern ice cores, look very, very similar. So there's some threshold somewhere in the middle of Greenland. But there are other features that clearly tell us we're looking at the same thing. This is the Younger Dryas transition I pointed out before. You can see the North Grip and GISP2 look very, very similar. North Grip and Neem look slightly different. Neem seems to have a different step, but it has the same kind of a step. So the same idea of a 1 degree C per year change for 5 years and then a plateau. But the plateau might have been different. In deuterium excess, which is a combination of deuterium and O18, I won't go into the details, but it's a very rapidly changing parameter, and we think it's tied back to the ocean conditions. You see here that the deuterium excess shift occurs about 1 to 3 years at all of these sites. This is the end of the Younger Dryas. It cruises along and drops. This is the end of the Younger Dryas at North Grip and Neem. I won't go into any kind of detail here. I do want to show you that this is the bowling warming in deuterium excess space. So these are two isotopes combined, cruises along, drops, and you actually get features in here that are very similar from location. So we're not looking, again, this is not noise. We're looking at signal in here. And this is a shift in 1 to 2 years of something fundamental in the climate system. All right, so I told you I would give you no answers, but I'll give you some speculation. All right. I had a postdoc, Jacqueline Flugerker, who worked with me, and we tried all sorts of models. We tried simple models. We tried complex models. We tried to get the model to make a change happen of the magnitude we were looking at in the time period we were looking at. So in other words, I wanted to see a change of 10 degrees Celsius, and I wanted to see it happen in anywhere from 50 years to 1 year. And we couldn't get a model to do it. And it's still true today. We cannot get these kind of abrupt changes to occur in our most sophisticated general circulation models. Now, I don't know why that's the case, but this remains a challenge. It remains a challenge for the models. It remains a challenge for the paleo community to try to understand what all this stuff actually means. So there are many striking features. They're fast. They're huge. Going from Mobile to Minneapolis climate-wise is a very big deal. And I haven't made a big point of this, but the stability of these states is remarkable. So keep in mind that you had a Younger Dryas cold period, which was 1,000 years long, that had a certain level of snowfall, had a certain level of temperature, certain level of dustiness, all this stuff. And then in a matter of a lifetime or less, you went to a totally different state that stayed that way for the next 12,000 years. So what keeps these things stable in their states? And this is where the ocean mechanism has come in very strongly over time. People have argued that this has to do with the turnover of the North Atlantic deep water, the Atlantic meridional overturning circulation. But what we have tried to do over and over again in models is put that into the model, run the thing, and see what happened, and we can't get the result that we want. So I think there's time or not time, but I've been thinking quite a bit recently about other mechanisms, and particularly atmospheric mechanisms. So I'm not going to give you any answers. I'm just going to give you today's current speculation, because why not? I think that there probably was a split jet stream at the time, and I think that perhaps that has impact on ocean circulation in ways that right now the models don't capture. Right? So in other words, could you have a situation in which you had, we think there was a very strong jet coming over the pole at the time, and that's because of dust that we see in the ice core, and we can actually fingerprint that dust to China, and we're pretty sure that there was a pretty strong piece of the jet stream coming over the pole. Could that have fundamentally changed the way that the North Atlantic was getting fueled with icebergs, or the way it was getting fueled with fresh water, or something going on there that then indeed impacted meridional overturning circulation or the North Atlantic deep water? So I don't know the answer to that. I'm just going to throw that out as a possible idea. I will point out, Bill said I was a data guy. I am a data guy. I also, actually one of my most recent publications was a publication on modeling the Pliocene. So I pointed out before that the Pliocene is a very warm time period. Models can't get it that warm either. This is another point where we're struggling with the models to figure out how do you make the Pliocene as warm as it was. And as it turns out, there may actually be a loop in here. One of the things that we found was if you took all the sea ice out of the Arctic, you could make the Pliocene warm. Big question is, how do you take all the sea ice out of the Arctic? And we don't know the answer to that question, but I'm beginning to think there may be something about the way the atmosphere circulates and the way the ocean circulates, that these two things might be tied together. So I will wrap this up. I'm not going to get into low I. I'll wrap this up with a slide that these days, even in scientific talks, I come back to this slide. Now this has very little to do with science. It has a lot to do with ethics, right? So you can, if you're expecting all science, you can turn off right now, and I will rant for a while, and then you can say, okay, turn it back on. We hear all sorts of stories about changing climate. We hear a lot of doom and gloom, and what I've shown you in this talk today is indeed we've got worries. We've got worries in Antarctica in terms of sea level. We've got worries in terms of the climate system being far more unstable and angry, if you will, than we take that we give it credit for today, that we include in our models, that we include in the IPCC projections, we include in all of these things. We've got an angry climate system out there, and that's not a good thing. Now, you can get depressed about that, or you can take a step back and go, what's the good news? Now, as it turns out, there's good news, right? And I'm going to tell you the good news. Right? In order for us to move forward on the planet, we've got to figure out how to live sustainably on the planet. And in order for us to live sustainably on the planet, we have to overcome certain hurdles. A big hurdle is the hurdle of the fact that we live on a water planet. When you live on a water planet, climate is always delayed. It takes a while to warm the ocean up. It takes about a generation, as a matter of fact, to warm the ocean up. So while we have 400 parts per million CO2 in the atmosphere today, we don't have a 400 ppm climate today. And we don't because we don't have. It's going to take a while for the ocean to warm up. It's also going to take a while for the ice sheets to melt. There's all these lags in the system. And one of the keys to dealing with that problem is figuring out how are we going to get one generation to actually value the next generation. The intergenerational ethics here are huge. So what my generation is doing is burning all the available oil and coal I can get my hands on, and natural gas, creating CO2 at high levels, and then handing it off to my kids. While, by the way, I say, and this is true, I love my kids. I'll embrace my kids. I say I love my kids. But do I show that? Not really. If I really love my kids, would I be doing this to them? And my answer, honestly, is no, I wouldn't. That there has to be a better valuation of one generation to the next. All right? That's one thing we have to overcome. Second thing we have to overcome is we have to deal with population. Now, this talk had nothing to do with population, but in the end, population is critical to dealing with our future on the planet and our intersection, if you will, with the climate system. What is the key to population? All right? Demographers will tell us over and over again, it's the equality of the sexes. Right? We live on a planet in which men run the show. And in many parts of the world, women are valued only for the number of babies they have. As long as that continues, you will not be able to deal with population on this planet. Unless you think we are doing so well here in this wonderful industrialized country of ours. Who was the first female president of the United States, class? When did women get the right to vote? This is a world which is got things turned around in terms of its relationship between men and women. And until that relationship becomes one more of equality, you will not be able to deal with population. Third piece of the puzzle is, as long as you have 2 billion people on the planet who are not participating in the economic wonderfulness of what we have today, the middle class and beyond, and indeed there are 2 billion people who daily either starve or don't get enough calories. They don't care about the environment, and they don't give a rat's patootie about climate. They care about where they're going to get their next meal. And they're going to care about putting shelter over their babies' heads. And they're going to care about feeding their kids. Right? So until you have better wealth equity on the planet, you're never going to get to a situation where you can control and deal with the big issues of our, as a collective species, valuing the planet on which we live. Now, I think it's good news that in order for us to live more sustainably on this planet, we have to actually value our kids in deed as well as in words, that men have to treat women better and share the power and the wealth on the planet, and that the rich have to actually treat the poor a little bit better. If we can get those three things under our belt, we can get closer to sustainability. Thank you for listening. I appreciate very much the time that you've given me today, and be happy to answer any questions. I don't know where to look. Fortunately, I said nothing controversial in the last. Yeah, Murat.
Yeah. So, we talked about climate change and the magnitude of the temperature change and the timing. Data is from Greenland. Are we talking about green climate, Arctic climate, global climate? How do we go from one to the other?
There are, I didn't, you know, in the time allotted, didn't have time to go and look at all the records around the world, but there are, particularly in the northern hemisphere and in the tropics, quite a few records that show, you know, cave records in China, ocean sediment records, Geological Basin, other places that show that abrupt climate change is not just a Greenland phenomenon. Were it just a Greenland phenomenon, we'd be talking about something different. It doesn't translate as well to Antarctica, as you know, that's one of the features of abrupt climate change we'd like to understand more about. Yeah.
I have a related question. When you talk about the temperature swings, is that mean annual or is that rain in the summer?
I don't know. I'm not sure we will know. More than likely, it is seasonally biased. Particularly if you think about when it gets really cold, you lose some of that winter precipitation. And so what you're looking at is going to have some seasonal bias. The longer answer to your question is that while the temperature is calibrated by a method that I really trust, which is the nitrogen-15 of N2, the isotopes are being used to give you the year-by-year changes. And the year-by-year changes in the isotope could well have seasonal imprints all over them. If you could imagine a year in which you didn't have a winter, you'd have a an isotopic composition that was pure summer. Okay, so just imagine that as a possibility. So the answer to your question is way more complex, but you do need to be careful about that. See how quiet we can be. No? Is there like beer waiting or something like that? Yeah.
Kicking methane
Yeah.
concentrations, you said related to the melting. Is it just equilibration of atmospheric methane with the meltwater that causes that?
Yeah. Yeah, you would just create a puddle at the surface and you get a little extra methane in there. Yeah, it's not, typically we try to go places, Bill, where you don't get melting to get gas records because, what we found in this far northern part of Greenland is that more than likely we're going to have trouble with that. So even if we got a perfect record of the Eemian, it will probably have melting in it because this is one of the coldest places we could go. So the Greenland ice sheet was quite different during the Eemian in that sense, in that it was more like, well, for example, the southern part of Greenland today melts frequently during the summertime. So the southern part of Greenland is probably a good analogy for what northern Greenland looked like at that time period. Yeah.
So how fast can ocean currents change? Don't they have a lot to do with the climate?
That's, the core of my challenge here is they can't, we don't know, but shutting down in 1 year, maybe that's possible, but I don't know. I mean, ocean currents have an inherent inertia. And certainly in the models that we've looked at where we basically, in order to get the North Atlantic deep water shut down, you put a whole bunch of fresh water out on the surface of the ocean. And that keeps the surface water from sinking to depth, right? And when you do that, if you do that in 1 year, you can get the system to shut off in 1 year. You can't get Greenland to cool off that fast. You can't get the whole climate system to then readjust in a very short period of time. It's also artificial, right? I mean, here we are dumping a whole bunch of fresh water out there. In order to keep the system from reestablishing deep water, I got to keep putting fresh water out there. So I got to find a hose with a very big tap somewhere and just keep pumping fresh water out there. It's one of the basic conundra? It's one of the basic problems that we have in trying to interpret these abrupt climate changes in terms of deep water formation. Keeping that system shut down is a hard thing to do. Yeah?
Yeah, along those same lines, I know it used to be they had to put in very unrealistic amounts of fresh water.
Yeah, yeah.
NADW, is that still the case?
No, we're able to put in more realistic amounts of fresh water. That's why I think, for example, if you ponder the idea that, if you've got a strong polar jet coming over, and I don't want to get too far into this because it's complete and utter speculation, but, if you're constantly pumping ice down into the NADW formation areas, lots of ice coming down in there, it's possible that if you just keep that air circulation turned on, you can keep pumping fresh water via ice into that area and keep that system shut off, as long as the winds happen. Which is why I went to the Pliocene for a minute there, because if you think about it, if there was no sea ice during the Pliocene, you couldn't have that mechanism. And so there's some hidden ocean mechanisms in here that we don't know about. Yeah.
So if the ocean currents and the jet stream changes, which kind of seem like they would be a gradual change over time, what's the next thing in the Earth system that you would jump to explain the rapid temperature change that could happen so quickly? That wasn't the jet stream of the ocean.
It wasn't. So it wasn't the atmosphere of the ocean? You're not leaving me a whole lot of planet to work with.
Well, I mean, it just seems like those are kind of gradual changes that would happen.
Actually, I would argue, I think the ocean has a certain gradualness built into it because of the just inertia of water circulation. I think the atmosphere is capable of some boom changes. And so I actually think the atmosphere is where we should be looking. That the problem, so here's sort of the conundrum here. The ocean has lots of inertia, but it seems to be capable of sitting in one state or another state. So the state issue seems to be answerable by the ocean. The speed issue can be answered by the atmosphere, but the atmosphere doesn't seem to me to be the kind of system that wants to stay in one state. So in other words, if we had a polar jet stream and then, 14,281 years ago, it went boink and never decided to come back, why? Is it really that much of a knife edge when it comes to atmospheric circulation? And I don't believe it, and I have trouble with it. And so you've got, two mechanisms, both of which can transfer large amounts of heat, one of which seems to have the ability to stay in states, but doesn't seem to be able to make things change fast enough for us. The other which can change rapidly, but doesn't seem to want to stay in states.
But maybe the contents of the atmosphere, not just the circulation.
Well, the atmospheric composition certainly changed. Dust changed. But I don't know. Certainly, greenhouse gases, for example, didn't change right away, and I don't think they would immediately change things anyway.
Dust change on that 10-year?
Dust can change in 1 or 2 years by order of magnitude. And that's a wind issue. You've got this strong. Clearly, what you're seeing in the record, I think, is a fundamental shift in atmospheric circulation. Why it decided not to go back and keep bouncing back and forth for 100 years or something like that. Why don't you see this crazy period, when no one would want to be alive on the planet at that time? But that doesn't seem to be what happens. What happens is the system cruises along and then boinks to another state and just stays there for 1,000 years. Yeah.
Do historical positions of the jet imprint themselves in any potentially sampleable way in the future in surface scale records?
A very good question. What we do in the ice core business is we look at things like dust and where it comes from. So for example, the dust that we see in Greenland during the cold periods has clay, and the clay composition is consistent with Chinese loess. And so that's why we think that either you had some mechanism by which that dust was picked up and carried all the way around the barn, or more than likely it was carried up over the pole. And so the idea of the polar jet comes from that, plus speculation. Going back to the 1970s when people first took a look at that Laurentide ice sheet and said, what is that going to do? In the early models of Manabe and all, what's going to happen to the jet stream under that scenario? And if you look back, there's some interesting papers that argue that maybe the jet stream split at that time. We don't see that so much in the modern models. Yeah, Bill.
Clear my throat to get your attention, but
Yeah, but you did.
I did, yeah.
The question I had is, you talked earlier about the continuous, right after the course retrieve measurements. Are those followed up by discrete measurements back in the lab, or does that sort of serve as, you do both, I guess?
A good question. On the NEAM ice core, we're doing both. I think the continuous flow methodology, which that's a whole other talk I can give. I think that's where we're going, and we don't need to do the cuts, discrete samples anymore. Continuous flow technology does a couple of things for us that's fantastic. One is you get the highest resolution you can get out of the ice core. If you're willing to melt at a low enough speed, you can get the highest resolution the ice core allows you to have. The other is that in a matter of about 8 months, we can measure a 3-kilometer ice core. That would take us 5 years under a cut and measure approach. So it's going to be a game changer. And the West Antarctic ice core will be finished soon. And it has, annual layering back 10,000 years, and it has ENSO signatures going back 40,000 years. And we can tell that now for the first time ever because we got these records.
That was one of the things I'd like to say. A lot of the ice core stories have always been presented as just so stories. It's just this way.
Yeah.
You're talking today, it's really revealing. It really got my attention when you talk about flops and overturns and things like that. And puzzling that stuff out. That's really clever stuff. So.
Well, this is what the Earth is telling us. And the question is, how do we fit it all together, and how do we make sense of it? And I don't know the answer to that yet. If I knew the answer, we'd have a very different talk.
Any other questions?
Give up.
Let's thank
Thank you.
Bill for